Hi everyone, good morning. I'm so excited to be here, see real faces. That makes it even more special. So today's topic will be Dual TOR use case for single NIC servers. My name is Kamini Santanagopalan. I'm a product line manager with Broadcom's core switching group. My co-presenter Lawrence Lee is the senior software engineer with Microsoft. But unfortunately, he cannot be in person today, so he will be remote, and he can answer any questions you might have. And I'll be playing his portion of the recording when it comes to that. So let's get started. So I'll just go over the use case, the data center use case, and where the pain point lies, and how we are collaborating with Microsoft in addressing the pain point, and then walk through the technical details. So as you can see, this is the classic data center topology, BGP class IP fabric. You have the tier 0 top of rack devices connected to tier 1 row leaf, and in turn, those are connected to spines and so on. We have a full mesh, and the key point to note here is all the nodes are connected to every other upstream node in a redundant manner, so that we don't have any single point of failure situations. So now, if we double click on the top of rack connected to the server racks, clearly there we have a single point of failure because there is no redundancy built in. The server rack is directly connected to the top of rack, and that is the problem area we are going to talk about today and explore options. So the classic single point of failure, we've all seen it. TOR is a pin where single point of failures is so common. And statistically speaking, switches do fail as much as we like them not to. And statistics shows that roughly 2% of the switches fail in the first 3 months. This 2% number may look small, but then when we are talking about hyperscale data centers and when we are having millions of network devices connected, this 2% quickly adds up, and it becomes a nightmare for the network operators. And we have also seen that 32% failure is seen, hardware failures are seen, and plus 27% failures are due to power issues. There could also be link failures, like the link between the server and the top of rack, that could also have some failures. And when you do the TOR upgrades, like when you want to do the software upgrades, that is a big pain point. So how do we do it? Should we carve out a maintenance window and talk to the organization and tell them that this is the window we'll be doing the upgrades in? That is so old style, right? That might not work when we are talking about a very high scale data center where downtime is pretty much not an option. So some of you might be thinking, okay, so dual TOR, so what is she talking about? We have MC lag, and people have been using it for ages. So what is so new, and what is she here for? So I completely agree with you. Let me explain. We have multiple options for tier 0 redundancy, of course. The classic one being MC lag, which majority of the enterprises uses, where you have the servers with 2 NICs connected to 2 top of racks, and you have the interswitch links between the switches. This works good. But here, the key thing to note is this requires 2 NICs to be on the server. And not all the servers have this option. Some are really old and might be coming only with single NIC. And you might have a large number of those that you cannot afford to go with the dual NIC or upgrade them. Similarly, you have the other option, distributed vSwitch, where this also needs dual NIC. And the performance is limited by CPU, so that's not, that is an option, but it's not helping our case. And there are other options like the single root IOV that also requires dual NIC, and that is also not helping our case. And you could do NIC offloading, but there it is all, the implementation is all vendor specific, and it could seem proprietary. We cannot, at least we are not able to utilize that method. And that's where the solution space where between single NIC and the TOR, the link there that is shown here, that is where we are focusing on today. And that's where Microsoft and Broadcom have collaborated extensively to come up with a solution. And I'll show you just in a minute as to how that is done. So in this diagram, we see the two top of racks running on Broadcom Silicon Trident 3 as an example. And we also have the server down there with 1 NIC. So what we are using here is a Y cable. As the name suggests, it's a MUX cable in a Y-like, Y shape, pretty much having two connectors on the top going to each of the dual TORs, and one connector connected to the server side. And you have the hitless MUX in between that can do hitless firmware upgrades and switchover. And this Y cable assembly is plugged into the TORs and the server, and thereby we can eliminate the need for dual NICs and go with this approach. And this is something that we have worked closely and tried to solve this problem. And now let me pause for a second and hand off to my co-presenter. Since he is remote, I'll be playing his video.
The active standby configuration on the cable is used to determine which TOR is responsible for sending traffic to the server. Northbound traffic is broadcast to both TORs by the cable, but only southbound traffic from the active TOR is sent to the server. Southbound traffic from the standby TOR is dropped by the standby side of the cable. As you'll see in just a moment, this asymmetry is what allows for automatic switchover during failure scenarios. Now we'll take a look at the mechanism that Sonic uses to determine which TOR is active and which is standby. Both TORs will send a continuous heartbeat to the server. The heartbeat is simply an ICMP echo request, which also contains a UID for the originating TOR as the payload. Because of the cable's design, only the active TOR's heartbeat will reach the server. The standby TOR's heartbeat is dropped by the cable. The server will then reply to the echo request that it receives. It will also take the UID from the request and include it in the response. The cable will then broadcast this response to both TORs, which then look at the UID contained within the response. If, for a given TOR, the UID matches its own, then that TOR knows that it is the active TOR. If the UID doesn't match, then the TOR knows that it is the standby TOR. Now that we know how the active and standby states are controlled, we can examine how these states affect the data plane traffic to and from the server. In our design, southbound traffic can only reach the server via the active TOR. When a T1 is routing a packet to a given server, the T1 can send the traffic to either the active or the standby TOR for that server due to ECMP routing. If the packet happens to land on the active TOR, then it can be forwarded to the server normally. If the packet happens to land on the standby TOR, the standby must send it to the active TOR to be forwarded. This happens via an L3 tunnel that is configured between the standby and the active TOR. Once the packet lands on the active TOR, it can then be forwarded normally. Northbound traffic is a little bit more straightforward. Anything that the server sends is broadcast to both TORs by the MUX cable. The active TOR will forward it to the T1 as usual. To prevent the T1 from receiving duplicate traffic, the standby TOR will actually program an ACL rule to drop northbound data plane traffic. That's what this circle represents. Next, we'll take a look at some of the changes that had to be made in Sonic to support this dual TOR use case. To manage the active and standby state on the TORs, a new container was added, the MUX container. This container is responsible for the previously discussed heartbeat functionality, as well as making sure that the TOR states converge during failure scenarios. New features were added to the orchestration agent, aka the orc agent, to manage the L3 tunnel for southbound traffic, as well as the ACL rules for northbound traffic. To accomplish these, the org agent had to interact with new PSI APIs and attributes, which we developed in close collaboration with Broadcom. Finally, we updated the transceiver daemon, which is responsible for directly controlling and communicating with the MUX cable. This daemon also exposes an interface that vendors can use to write their own cable drivers. This provides Sonic with a uniform way to control cables from multiple vendors. Now let's look at how this dual TOR setup deals with TOR failures. For this scenario, let TOR A be the active TOR initially, and TOR B is the standby. If A somehow becomes unhealthy, which could be anything from a cable break to a loss of power, the heartbeat from this TOR will not be received by the server, which in turn stops sending heartbeat replies to the TORs. TOR B detects this loss of heartbeat and begins the switchover process. B will tear down the L3 tunnel used to forward southbound traffic, as well as the ACLs used to drop northbound traffic. Now, TOR B's data plane configuration is ready to forward traffic. B will then signal the MUX cable to make itself active, allowing traffic to continue flowing. And here's a quick animation just to help illustrate the switchover process. Here, the failure scenario is a break on the active TORS segment of the cable. The standby TOR detects the loss of heartbeat and tears down the tunnel, as well as the ACL rules. It signals the MUX cable to make itself active and continues forwarding traffic. Separately, the initial active TOR will detect the cable break and change its own internal state to standby. It will create the L3 tunnel to the new active TOR, and that will allow this TOR on the left to forward any southbound traffic to the new active TOR, which is on the right.
All right, thanks to Lawrence for the deep dive. So now, again, in this whole project, Microsoft and Broadcom have closely collaborated on supporting this whole dual TOR use case. Broadcom has provided us the size support for this project for T0 devices, the Tier 0 Trident 3 and Tomahawk 2 devices. And I'll also show you the list of all the PSI APIs and attributes that have been contributed thus far for this project. And outside of this project, I would like to highlight that Broadcom is overall committed to Sonic and PSI activities. We have had close collaboration since 2016 from the PSI level. And since 2019, we have been actively participating in the Sonic upstreaming and contributing to the community as well. And significant contributions we have made to the PSI specification in 2020 and 21. Like such as the VivoQ architectures or the tunneling mechanisms, like how Lawrence talked about the bounce back link between the standby and the active, which goes through IP and IP or VXLAN. So those PSI contributions, PSI specification improvements and enhancements we have provided. And we are also continuing to partner with Microsoft on extending Sonic and enabling them in the new use cases, additional use cases. So this is just the list of all the PSI attributes and APIs that have gone specifically for this project. You can take a look at this offline. These are all specific to tunnel creations and how everything is handled. We are almost at the end of the presentation, so I'll just quickly segue into demo. That shouldn't take too long. So.
Now we've come to the demo portion of our presentation. This is the topology of the setup that I'll be using to demonstrate our design. So we have two TORs connected via a MUX cable to a downstream server. The TORs are both connected to a T1 switch. And just for the purposes of this test, I've added an extra test server connected directly to the T1. So when I send traffic during the test, I'll be sending it between these two servers over a TCP connection. And just note that this downstream server is connected to port Ethernet 0 on both of the TORs. So first, let's take a look at the state of both TORs. So on this one with the host name ending in UT0, which we can call the upper TOR, I'll run this command showMux status for port Ethernet 0. And we can see that this upper TOR is currently active and healthy. And healthy just means that this TOR is receiving the heartbeat response from the server. Running the same command on the lower TOR here, ending in LT0, we see that this TOR is standby and healthy. So now, on the server, all the way over here on the right, I'm going to start an iPerf session and just send a few seconds of traffic. So this will serve as our baseline. There's no instability or no switching going on with the TORs when I was sending this traffic. So we'll see that the bandwidth used by iPerf is relatively consistent. This is CPU dependent, so based on the CPU usage of the server, this will vary a little bit, but we can see that it's mostly consistent with no major dips. So next, I'm going to send a little bit more traffic for a longer period of time, and on this lower TOR, which is currently standby, I will run a command to manually make this TOR active. And in production scenarios, what this lets us do is go to this upper TOR, which will be standby after I run the command, and we can do maintenance and upgrades on this TOR without disrupting traffic to the servers below. So that is the command that I'll be using. So I will run the iPerf session and trigger the switchover at about the halfway point. All right, so we triggered the switchover. And now that this iPerf session has finished, we can look at the bandwidth of traffic that iPerf was able to send. For most of the test, it hovers between 10 and 11. And right when I triggered the switchover, we can actually see this dip to about 10.3. So the switchover will cause a little bit of traffic to be lost. However, that is definitely preferable to losing access to these servers altogether. And you'll notice that the TCP connection did not get dropped, and iPerf was able to go back to using the full bandwidth after the switchover was finished. So now, if we check the state on this lower TOR, we can see that it is active and healthy. And on the upper TOR over here on the left, we see that it is standby and healthy. So just real quick, I'm going to run some commands to reset the TORs to their original state at the start of the demonstration. And then I will simulate a failure scenario, and we can look at how the system behaves under duress. So I've reset both TORs to the original states. The upper TOR is active here, and the lower TOR is standby. So I'm going to send about 20 seconds of traffic with iPerf again, except this time on the original active TOR, I will be simulating a link failure by shutting down the Ethernet 0 interface. Get that command ready. And I'm going to go ahead and start the iPerf session. And once again, at about halfway through, I will trigger the failover condition. We'll wait for the session to finish. And once again, we can see right around the halfway point when the switchover occurred, there was a dip in the bandwidth of traffic that iPerf was able to send. It went from anywhere probably around 11.5 to 9.5. So because this is a failure condition, we do expect to lose a little bit more traffic than a planned manual switchover. However, once again, iPerf was still able to maintain the TCP connection, and after the switchover had completed, it went back to using all of the available bandwidth to send traffic. Finally, let's take a look at the state of the TORs after this failover scenario. So on the lower TOR, we see that it is now active and healthy for Ethernet 0, which is good because this means that the failure detection mechanism that we designed was able to switch this TOR to active and maintain connection to the servers. On the upper TOR, which experienced the failure, we see that the status is now standby and unhealthy. And this is actually expected now after the failure because this TOR is no longer receiving the heartbeat responses due to the simulated link failure. So hopefully now everybody has a more concrete understanding of how our design works to mitigate failure scenarios that would otherwise take an entire rack of servers offline.
All right. That's pretty much what we had to cover. Questions, feel free to use the online window as well for any questions you might have.
Is that MUX cable passive or active? Is there something you're programming in that to do some of this, or is that a passive cable?
It's a passive cable.
So then is there something changing in the NIC? Because there would be different peers being utilized, correct?
So it still acts as the active and standby, right? The active and standby controls are there. And the chip that is in the MUX cable, that can do hitless upgrade for you. So that issue you will not run into that.
So there's a chip in it.
Yeah. That's the Broadcom chip that goes in the Y cable.
Okay.
Yeah.
We have time for one more question.
Oh, I have one question.
Yeah.
You mentioned about your failure rate overall is about 2%.
Okay.
About switch. Is that the consistent in that way, or do you have any plan to improve that? Because the 2% of the annual failure rate is, for me, is pretty high for us.
Yeah. That's the reason why we actually collaborated on seeing what can be done to improve and whether this method really works or not. That's the reason. In an effort to improve that percentage, the failure rate, that's where the whole effort was.
Thank you.
Yeah.
All right. Well, thank you very much. And I saw
you.
actually quite a few questions come online, and I
Okay.
believe folks were answering, Lawrence was answering questions online as well. So
Sure.
if you have more
Thank you,
questions,
Lawrence.
please go ahead and ask those online. And thank you very much.